Okay, so let's keep going. All right, so we're going to find the general solution for each of the following homogeneous equations. So, yeah, just the general solution is going to be, uh, these are second order, right? So, homogeneous means that this all equals 0 when you get this. So, in general, you're going to want to make an auxiliary equation. This is linear homogeneous with constant coefficients, right? Because it's just 1 minus 7 minus 18, so that fits that criteria. So there's basically going to be three cases. Case one is you're going to get two real roots from your auxiliary equation, or you're going to get a double root where it's the same number. And then you're going to have to, your general solution is going to look like this. And then the other case is when you have complex roots, so you get square root of minus 1 in there, so you're going to use this magic Euler formula here, and then we're going to get this. So let's just go through the different cases, because I think they're all represented in this problem set. So, yeah, this is, first of all, that's an r squared. Okay, so r squared minus 7r minus 18 equals 0. So you can see where this is coming from. Basically, the number of ticks is going to be the powers that you're dealing with. So anyway, this one factor is easy enough. So it's minus 9 and positive 2 for these. So you get 0, so your roots are going to be 9 and negative 2. So your general solution is going to be this C1, which is a constant. You can get these if you have an initial value problem. We weren't given one, so this is our general solution. Anyway, so yeah, it's 9, so it's RT, and then the second RT. Okay, so this one here, our aux equation is going to look like this. So we're going to have complex coefficients here because our discriminant is negative. So anyway, so we're going to divide this by 2, and then this is going to be 2i. So we're going to divide that by 2, and we're going to get this as our r's. So in this case, you want to have alpha is going to be your real component, and beta is going to be the absolute value of your, well, your imaginary component. And anyway, so your general solution is going to look like that. It's e to the alpha t times c1 cosine beta, which is 1 in this case, so beta t plus c2 sine beta t, just like this formula here. Okay, so this one here, our auxiliary equation is going to look like this. I'm just going to divide by 2 to get this here in a easier form. I guess it's all the same really, but anyway, so then I solve for my roots, so I get r1 equals 3/2 and r2 equals 1/2. So this is our, there's just two real roots, so it looks like this. This one here, that was like a 1, it was supposed to be a y. When he typed it out, it was wrong. So anyway, we got this. I'm going to divide by 4 to get this. Turns out, yeah, I'm going to get a double root when I do this one. So r is going to be minus 1/2. So this is our general solution. It's c1 times e to the rt plus c2 t e to the rt. And then this one is just a hairy one because it's cubic and no one likes doing those. There's like rational root theorem you can use and like synthetic division. I don't know if they're exactly the same thing. It's funny because I've probably taught it to myself about 4 times in the last like 3 years and I still don't remember how to do it. This isn't even, I don't even think it's proper. I could be wrong, I'm not sure, but anyway. What I've done is I just take I always try 1, because 1, I mean, if they're going to give this to you and you don't have a calculator, 1's probably going to be a root. So let's just try r equals 1. Plug it in. Does it equal 0? Well, it sure does. So r equals 1 is a root. Now, the rest, knowing that 1 is a root, take the coefficients of this. So that's 1, minus 3, 7, minus 5. You're going to say, oh, God, how do you do this? You know, it's funny because, like, I don't even remember long division. I'm doing, anyway, whatever. So, 1 minus 0 is 1. Why do I have 0 there? Good question. But the rest is going to be, this 1 comes up here. minus 3 plus 1 is minus 2. The minus 2 comes here. 7 minus 2 is 5. And then this 5 goes here. 5 minus 5 is 0. If it divides evenly, these are going to be your coefficients. 1, minus 2, and 5. So that's how I get this. And remember, r equals 1 was a root. So we get that. So then we're going to take this and get this. So turns out we have two complex roots and a real root. So with alpha equaling 1 and beta equaling 2, this is what our general solution is going to look like, right? So this is the real root, and this is the two imaginary roots. Okay, so this one is an initial value problem. So here's our auxiliary equation. So it's going to be plus or minus 3i. Alpha in this case is 0, so it's e to the 0 c1 cosine beta, which is 3t, plus c2 sine beta t. E to the 0 is 1, so you can just write it like this. So now let's take the derivative of this general solution. We're going to get this, and we're going to use this initial value here, y of, so now we've got the two things that we want to check our initial values with, because we just want c1 and c2. You don't actually have to like go and take double and plug them in. I was going to do that when I started this, but yeah, like why should you have to? You just have this, right? So yg is this, so let's plug in 0. That's going to equal 1, so 1 equals c1 cosine of 0 plus c2 sine of 0. These are trig functions, so life's easy for us. We get c1 equaling 1, and then y prime of 0, so we just take this one here. I'm going to plug in zeros for all our t's, and we have c1. So, but c1 is, well, sine of 0 is 0 anyway, so c2 is going to be 1/3 when you solve it like this. So this is our general solution, right? So yg was this. Boom. That's it. Another initial value problem. So again, these are constant coefficients. Go ahead and set this up. We get a double root here. So this is what our general solution is going to look like. And we have y prime of 0. So let's just take the derivative of that and get this shit. Y of 0, go ahead and plug in zeros here. C1 equals 1 again. And y prime of 0 equals minus 2. And so we got c1 plus c2 equals minus 2. And we said c1 was 1, so then c2 has to be negative 3. So there's our general solution, right? So you just go back up to here and plug in your c1s and c2s, and you'll get this. Okay, solve the differential equation y double prime plus 4y equals sine x by undetermined coefficients. I hate doing this stuff. It's so long and tedious. But anyway, okay, so this one's easy enough to find the roots for, because this has to be I, because it's got to cancel this 4 out, right? So now we got alpha equals 0 and beta equals 2, so our y, I just call it yh because it's the solution to our homogeneous. Because basically, I didn't actually write this out, but if you take the solution to your homogeneous and add a particular solution, we're using the undetermined coefficients method to do it. So you're going to have a particular solution and then a solution to your homogeneous one. If you add those two together, you're going to get y. I could not tell you why that is. At some point, you just got to stop asking because you got 6 courses to do. So anyway, yh is going to be this shit. So the particular solution is going to be based on this, right? So in general, you're going to have some constant times cosine x plus b sine x because of this. Now, we're going to take the derivative of that and the second derivative, and then we're just going to take this original equation. We're going to take y double prime, which is this, plus 4 times y, which we said yp was this, and then we're going to simplify this out. And then we got to make it, we're just comparing the coefficients here. So we got a sine x here, so we know that the cosine x one is not there. So the only way to make that 0 is to make a equal to 0 here, and then we get b is going to be 1/3 because that's got to, sine x has to be sine x when you get b there. So now y is going to be yh plus yp. That's what I said before, right? So there's yh. Now yp is, well, I didn't write it, but yp is this, but we figured out a and b, so you're just going to plug that in. So it's going to be this plus, remember, b was 1/3, and so that's our general solution. Solve the differential equation y double prime minus 4y equals e to the x plus e to the minus x by undetermined coefficients. So here's our auxiliary equation again. This time we get two distinct real roots, so this is what our homogeneous solution looks like. Now our particular solution is going to be, whenever you have an e to the x here, or e to the whatever, you're going to have a e to the x plus b e to the minus x in this case, right? Take the derivative, get this. Take the second derivative, get that. Take these are now what you can plug into this. So y double prime, there's one of those, so we're going to have one of those in there. There's minus 4 of these in there, and that has to equal this stuff. So we go ahead and do that. So y double prime, this, minus 4y, and then we're going to just even these things out. As we say, it has to be this. So the e to the x one has to be negative 1/3, because it just needs to be e to the x equals e to the x. And then e to the minus x, b is also going to be minus 1/3, because we just have a positive e to the minus x. So now this forms our particular solution. You got a and b, you plug those into here, and you're going to add that to the solution of the homogeneous, which is this one. So that's how you get this result. Okay, solve the differential equation y double prime plus 4y equals sine 2x by undetermined coefficients. So again, same recipe, auxiliary, this again, plus or minus 2i. So with the imaginary roots, this is what your general, or your solution of the homogeneous is going to look like. Now our particular solution, sine 2x, since 2x, you can see the 2x, our root, it matches our root. So to match this, we're going to have, normally you just have sine 2x and cosine 2x times a couple constants, but now you have to multiply by an x because it's one of our roots. So now you're going to distribute this x and you're going to get this. Now you're going to take the derivative and take the second derivative. Now you have this horrendous looking bullshit. So now we're going to take one of these god-awful things, and 4 of these ones. So I'm just canceling shit out. I can reduce it down until I get something that's like this, and then clearly b has to be 0 because there's no cosines in that thing, and it's going to equal sine 2x, so that's going to be a is minus 1/4. So then our general solution is our particular solution, which is this with the a's and b's that we found, added to the solution to the homogeneous, which is this one. So that's going to be our solution for that. Solve the differential equation y double prime plus y prime minus 2y equals x minus e to the minus 2x by so again, doing the same thing. So set up our auxiliary, r squared plus r minus 2 equals 0. Now we get two real roots. There's our homogeneous. So the particular solution, anytime you see an x, it's going to be ax plus b. And then this is not multiplying, this is just adding to it or subtracting, whatever. So it's going to be a coefficient times x e to the minus 2x. Why? Because minus 2 matches one of our roots, so that's why this x gets multiplied here. Otherwise, it would just be c e to the minus 2x if one of these roots wasn't there. But it is, so that's why we multiply by x. If you had a double root, it would be x squared, right? Because you'd have that root twice. But anyway, in this case, we have two distinct real roots. So that c looks like a bracket. That's what I was confused. All right, take the derivative, take the second derivative. There's our original equation. So we're going to have one of these, and minus 2 of these. And that's going to be equal to this. Again, cancel as much shit as you can. Now we're going to have something that looks like this. So c is going to be... Okay, so the e to the 2x has to match this. So c is going to be 1/3 because it's negative, right? Okay, so then we got our c. A is the only one that has an x, so that means it has to be minus 1/2 because it's just a single positive x over here. And then b has to cancel this a out. So if we have if a is minus 1/2, so that's, imagine that's minus 1/2, then this is going to have to be negative 1/4 in order to cancel this a out and leave us with what's over here. So that's how you get this solution. So again, we have our coefficients. You take yp, plug it in, and then you're going to take your solution to the homogeneous and plug that in too. So that's why. Write down the complementary solution yc for and the correct particular solution yp. So yc I've been calling yh this whole time. So if you see yc and yh, I think they're used interchangeably, or I'm just calling it yh because I probably don't know any better. Complementary. Okay, I'll just write yc's from now on. I guess it doesn't matter. Anyway, so don't solve for the coefficients. God, no, you wouldn't want to do this. For the problem, this equals this bullshit. So you get y double prime. Just get your auxiliary equation. Oh, looks like we got a double root. So anywhere where you see one of these in here, you're going to multiply by an x or an x squared, depending on how many are there. So, okay, so what's our first term? 2x. So normally you're just going to have ax plus b for that. Then what do we have? X squared. Well, that's going to be cx squared plus dx plus e. All right, so anytime you have a polynomial, just count down until you get to the 0. What's the third one? X squared plus x to the 5th times e to the x. So the x it's a 5th degree polynomial, so it's going to be 5, 4, 3, 2, 1, 0. And then I'm just going alphabetically up. So then we got L e to the x, right? Because it's multiplying, so that goes here. Now, e to the x, r equals 1 wasn't there, so we're not going to multiply this by x, so that's okay. Now what's next? 7x squared e to the minus 3x. Well, that one's showing up as our double root. So we're going to have to multiply by, not just by x, but by x squared, because both of our roots are represented in this one. So then we got, let me see, where am I? There's the polynomial. It's degree 2, so 2, 1, 0, but that's not a 0, that's an O. And then p, because there's another constant that you have here, e to the 3x, but because e to the minus 3x, and the minus 3 is represented in our, what do they call that? Complementary solution. So we got to multiply by x as many times as it shows up as a root here, which is twice. So that's x squared plus x sine x. Well, there's x, so it's a first degree 1, 0, and then because that is indicative of complex roots, which we don't have, but we still have this general form. So that whole thing is what that particular solution is. God damn. All right, so find the complete solution of the problem y double prime minus 4y prime plus 4y equals that crap. Okay, so this one is one where we want to use variation of parameters. I wonder why. Oh, because I don't really have an answer for this. Because this is x to the minus 4, right? So I don't think this is going to work when we have like negative. Because you just, what do? Just keep decreasing down to infinity? I don't know. Like you'd have like, you know, an infinite amount of coefficient. I don't think it works like that. Okay, so anyway, find the complete solution of this problem. So get our auxiliary equation as normal, right? So we got a double root here, so our homogeneous solution looks like this, right? Now, variation of parameters looks like this. When it's in this form, y double prime plus a function of t times y prime plus a function of t times y equals a function of t, or x, whatever. This is our function of x. That's our function of x, and that's our function of x. So the particular solution is going to look like this. v1 y1 plus v2 y2, where v1 is this. v1 is the negative integral of y2. So remember, 1, 2, and then 2, 1. Don't get those confused. 1, 2 has the negative sign. So it's y2 times g of t. What's g of t? This shit, right? This stuff when there's nothing in front of the y double prime, right? It has to look just like this. Times g of t divided by the Wronskian. What's the Wronskian? Well, it's the determinant of y1, y2, y1 prime, y2 prime. Well, I'll show you in a minute. So there's the homogeneous solution. Anyway, and V2 is going to be this. So I go ahead and I get this. Well, now I've got Y1 and Y2. So now the Wronskian is going to be the determinant of this shit. So it's Y1, Y2, Y1 prime, Y2 prime equals, so there's Y1, Y2, Y1 prime. So you just multiply by 2, and Y2 prime, they're going to do, there's two, or what do they fucking call that? I forget what it's called. Not the chain rule. Product rule. Jesus. Anyway, okay, so that's this. Well, what the hell's that? Okay, well, it's that times that minus this times this. So it's that minus that. Oh, look, the Wronskian is not horrible looking. Okay, great. So now our particular solution, again, we said was v1 y1 plus v2 y2. v1 is going to be the negative integral of y2, right? Because 1, 2, right? So y2, what did we say y2 was? X e to the 2x, x e to the 2x, times g of x, which is this. So I want to see e to the 2x over x to the minus 4 down here. E to the 2x, x to the minus 4, divided by the Wronskian, which is e to the 4x. So there we go. So when we multiply these together, that's going to be e to the 4x. That's going to cancel. And then this x is going to cancel one of those x's. So we get x to the minus 3. So that's going to be this, right? Because it's divided by minus 2, but there's a negative here. So this is v1. And v2 is going to be, v2 is the integral of y1 times g of x, which is e to the 2x over x to the 4th, divided by the Wronskian. So then that's going to cancel out. So we get x to the minus 4 dx. These are linearly independent, or I don't know. These these go into our particular solution. So you take these. So v1, which is this, there's v1 times y1, which is e to the 2x, plus v2, which is this, times y2. Why don't I have a negative sign there? I'm not exactly sure why I don't have a negative sign there. I may have made a mistake there. Anyway, it's added, right? Yeah. Anyway, I think that's supposed to be a negative, because x e to the 2x is y2. It's not negative x e to the 2x. So yeah, I think that's supposed to be a negative. Anyway, so that forms our particular solution. We're going to just take that. We're going to add it to our solution to the homogeneous. That forms y. That's the trick to all of these. So, okay, so now we got one worksheet left. How much time do we have? I'm going to come back in another video.